Quantum Foam, Episode 18, String Theory.
Quantum foam.
Physics. Physics is at the foundation of all the mathematical principles that guide the heavens. You have to understand physics.
More than likely that's not going to happen, but
Forces which govern the universe. Physics.
we are taking a moment here to assess some major problems that have been going on in physics and science since antiquity. Things have been described by the Greeks becoming accurate as we do better and better science. And so this is the point we're at now. So we have some pretty daunting tasks ahead of us here. We're going to attempt to go over the popular topics that can describe string theory this episode, and then we will take a look at other approaches next to try to find one that is more accurate than what is currently available. So what exactly is this string theory? Everybody's heard of it. They kind of sort of know what it is. It has to do with strings. It's the premise that everything is made of strings. Every subatomic particle constituent is made of strings that vibrate at certain frequencies that give the properties to the particles that we see. Using the tools within this theory that have been established, we are doing loop corrections. So we're going to have to take it slow, and I'm going to try to leave out as much bullshit as I can so we can get the main points across. How do we get these main points across? Let's start out by going over the history or the general progression of string theory from the beginning. They separate them in 4 different phases. First phase, 1968 to about 1973. This was sort of in the pre-cookup era where everybody was hadron crazy, as they say. They were just getting some of the colliders up and running. They were just getting CERN stuff cooked up. They were getting the linear slack collider up and running. All of these things were of a new science. So these theories started to get tossed around in back halls in math departments. Phase 2. What happened during this phase? Not really a whole lot. They were fundamentally describing the dimensions, and they were going up to 26 dimensions. They had various flavors of string theory. They say about 5 of them that they eventually were able to get refined down to the point where it was a coherent theory. But I gotta admit, we are scarcely prepared to cover these very, very complicated and very daunting tasks and subjects. I mean, what we do is 9 spatial dimensions, 1 of time and 1 of M theory, which makes it the container, sort of. There's a larger technical explanation for it, but I am not going to go into that right now. What can we really go over? We don't even know what a Laplacian is. We don't know how to put that into a delta F, XYZ shit. And then we got to go into S matrices and T matrices. Oh, man.
I would hate to be you right now. Break it down into some smaller pieces. It really isn't that hard.
All right, so let's just quickly go over the phases of string theory to give a timeline of how it went down, looking back from this point. So this is taken from a thesis to get a PhD in physics from somebody from Mumbai, July of 13. And it's like, this particular person, their thesis was 150 pages, man. I mean, is that the same as 500 hours? I better get going on this stuff. They get into the math in this, but I haven't done that yet. But I just kind of have to reevaluate what I really want to look into with this, because we can go so deep into this, and there are so many ideas that I don't even know where to start. We might actually take a look at this thesis later on. This is really just a mathematical and technical representation of phases. Pretty standard. It's a study of what happened in string theory, the progression of the theory, and the growth of the theory itself. I'm not going to pull much from that. Let's just go with something closer to like a brief timeline.
There were a lot of mathematicians who thought that the world could be fully described using only math. That's not really a new idea.
Okay, so in 1921,
that is where it starts.
Kaluza-Klein theory was put together, and this essentially allows 4D space and above, which means with time, 5 dimensions and above. Now, I only want 5 because you only need 1 more, and that's just to describe the container, so it's really not anything but a parameter.
Your version of Kaluza-Klein space is somewhat different than conventional representations.
And so, either way, this is not an old idea. This idea came around in the 20s, last 20s, and very fucking important, the beginning of string theory, because string theory relies on higher dimensions and a background-dependent grid lattice, a grid of space-time, point-particle, 3D Cartesian grid, and it relies on higher dimensions that are folded and twisted or unobservable by us. So what else? There's the big shots, Yoichiro Nambu and Leonard Susskind. There was also Holger Nielsen. I think he added some stuff about the strong force. This is way, way, way back when, the very beginning. I mean, supersymmetry, which is a fundamental idea of superstring theory. Oh, man. He's doing it again. I'm going to have to...
Knock, knock.
You got to be kidding me, man. Who's there?
Irene.
Irene who?
Irene and Irene, but still no one answers the door. Haha, funny, right?
Come on, man. He's trying to go over all of the technical stuff involved with string theory. Cut the man some slack.
Huh, thanks.
You guys suck.
Yeah, I don't know, man. It's kind of funny. But let's get back into this string theory stuff. Supersymmetry, discovered in 71, kind of put together. 74, string theory predicts gravitons. We start to get this idea about gravitons and how we might be able to unify gravity with the other forces, because right now we can get all the other forces to work in various mathematical structures, the strong force, the weak force, and the electromagnetic force. In and of themselves, we can describe them. Once we put them together with gravity, all hell breaks loose. And so, all hell breaks loose, all hell breaks loose, all hell breaks loose, all hell breaks loose. 1980, Michael Green and John Swartz start to do some revisions with this string theory stuff. Now it's actually starting to become a full-blown theory, and not just some shit kicked around in back halls and stuff. So the first revolution, 84, they were able to get some of these so-called quantum problems solved. They had quantum anomalies.
Not completely figured out, you mean?
In 84, the revision, they were able to get past it. So everything that happened thereafter was in the third phase. But the current version of string theory, what we know it as now, came out in 95 from Townsend and Witten. And this...
There were others too.
Sort of brought to light this M theory and the issue of duality, wave-particle duality. It's still a freaking problem. Unsolved. But Einstein and everybody agreed that wave-particle duality is actually a thing.
Probably not the same thing as dualism.
But the duality we're talking about here is as it applies to string theory.
This idea of duality has been gnawing at us natural philosophers for centuries. I thought that the ether vibrations in periodicity on light particles as they passed through thin films of substrates had something to do with this subject.
Andrew Strominger and Kumramvatha, they accounted for it mathematically.
I could have done better calculations if I had the computational machines that you have today.
So that really put us into our current era of string theory. It's sort of losing its steam these days. Keep in mind, we're just briefly touching upon this stuff. Without getting into a lot of these things, each one of these we need to go over.
There are a lot of theories that have led up to what is understood in string theory as a whole.
Perturbative theories, non-perturbative theories.
Maybe begin with perturbation methodologies.
This is definitely more your forte.
True.
A perturbative method is where you can basically plug all your stuff into Taylor series and describe it all mathematically. There are some things that we are not able to do this with because we know the value is non-zero. That requires a zero value. There is a difference between them, but string theory tries to focus on non-perturbative.
We have come up with grand explanations using string theory, but, as you were saying earlier, we don't actually know if these math boxes that we create actually do, in fact, describe the reality around us.
What about the formal theories? The ones that have at least been proven mathematically.
And so there's also ADS/CFT, anti-de Sitter space, as it compares with a conformal theory. The anti-de Sitter space is your string theory structure, and your conformal field theory would be your Maxwell stuff or Einstein equations or whatever you're doing that deals with your gravity.
Right. Invariance. The fact that during the calculations, certain mathematical computations do not vary, while so-called conformal transformations are occurring. The invariance means that it can hold up against physics that is said to be known and understood.
There are different mathematical equations where they heavily rely on this. String theory does.
Maybe we should just go into some simpler ideas. How about harmonic functions, stuff with heat conduction, or steady-state heat math solutions? there is a very complicated foundation which string theory relies upon.
Poisson's equation, Laplace's equation, or Laplace, delta squared F equals 0. I suppose a little bit can be said about these Laplacians. It's just a mathematical trick that can be used to filter images. And so the Laplacian of an image with a certain pixel density is essentially a filter because certain areas of the graphs within these Gaussian values, it's approximating a Gaussian smoothing filter. So the 2D isotropic measure of a second spatial derivative of this picture, of this image. The Laplacian of the image highlights regions of rapidly intense change within the image, and so it's often used for the detection of the edges of certain areas that you're dealing with. They use zero crossing edge detectors to find these edges. So that's the critical points within your graph, essentially. It's applied to an image that's first been smoothed with Gaussian filters to reduce the sensitivity to noise, because using these Laplacians on a math box of an image can sometimes increase the noise. And so using these two variations together can be done in a single operation, but it's actually two. You do this to it, you do the Gauss thing to it, then you do the Laplacian thing to it. And so this is something that's a little bit separate from how they're applying it in the string theory. However, it's a similar thing because it's basically just a math trick that describes part of a function. And so that's sort of an idea of what it is.
Much of this stuff is done using computers, but we have to know the underlying physics in order to make steady progress. Approximating reality is all we have been able to do in the past. I hope that changes soon.
A 2D Laplacian of a Gaussian function, they call these an log.
Logarithms.
Dealing with this Gaussian, it's essentially the Mexican hat thing.
It's so weird that the graph actually resembles a sombrero.
The A controls the height of the curve's peak, the B is the position of the center of the peak, and the C is Gaussian RMS. That controls the width of the bell section. These Gaussian functions are often used to represent the probability density function of a normally distributed random variable. There's an expected value.
Yes. The expectation value that you mentioned earlier. They need to have one of these in order to make sure they are dealing with the correct space, or the correct region of space-time, etc.
And there's variance. And so there's different forms that you can write these equations, but that's just a little bit of background on the Gaussian function, or the Gaussian. So the Laplacian is a Laplace function, or a Laplacian. And so they often apply both of these things to your structure for the purpose of describing the variance or invariance, to make sure. So there's lots of reasons you can use this for. And so these are how we can actually do the math with these multiple dimensions. There are parametrized functions within these big math structures that describe Calabi-Yao manifolds of twisted up higher dimension space. So we're able to count up scalar multiples using some of this math. There are different ideas within string theory that are important. There's the holographic principle, holography, and what actually allows us to describe the higher dimension spaces and what types of spaces you're going to be using. Minkowski spacetimes, anti-de Sitter space, positive space. A little bit needs to be said about the space-time in general. Space-time can be described as our 3 or more dimensions plus time in a single n-dimensional manifold. And for this case, it would be a 4-dimensional manifold. The laws of physics are invariant when we set things up like this. So this invariance means that each frame of reference of a space-time is considered identical to one another. Being identical in all inertial systems means that each of these frames do not have acceleration. They are non-accelerating frames of reference. So this is all based on relativity stuff.
Time warp-richer stuff.
Speed of light in a vacuum is the same for all observers regardless of the motion of the source. So that's how you can have somebody going half the speed of light and the other person stationary, and then those two relative to each other, and then the person who's going half the speed of light, they're still seeing the speed of light the same speed from their point of view because they're essentially squished up like a wave, kind of, because of their speed relative to the other person. And so this invariance is a very important thing because we need to know if things are identical when comparing them. Depends on what we're doing. And so one of the things that they claimed that had been done by string theory was being able to describe the black hole entropy, which was pretty nice.
I really hope one day we are able to find out the mysteries of these black holes. They have to be a gateway to another universe. They just have to be.
But for the most part, we have a decent understanding of that, but we still don't know what's inside of the black hole.
There is more we still need to find out, but we know that the surface area of the black hole is very important. Bekenstein and myself did much work on this involving entropy.
There must be some kind of pattern, probably, to the chaos within the chaos within the chaos. All right, we are about halfway through episode 18, String Theory
of quantum foam. Quantum foam.
Now, how do we get anything out of these black holes if light can't escape and light doesn't even have mass? Photons don't have mass. How can gravity be so strong that it can pull back other massless particles? Questions like these have very technical answers, but they're not really the answers that we are looking for either. And so what string theory sort of tries to do, it is a grandiose group of mathematical papers and structures that help define new unitary spaces, like a unit circle with 0, 1 right on the origin. You're making a unit space, a unitary space for a higher dimension grid. So the way they do some of these, they create Hilbert spaces. And part of the real work that's done, all these papers that are coming out all the time, what they're really doing is applying something called an inner product and seeing how that relates to the Hilbert space using some sort of normalization. But your Hilbert space will help you lead to...
Yeah, but what is it?
What it is a finite orthonormal math basis, which can describe a state. And what that state would be is your unit vector, essentially. And so the goods in your Schrodinger equation is your Hamiltonian. And so this Hamiltonian, it's your operator in your psi equation, which can describe your unit vectors, describe the spaces that you're talking about. The S duality and T duality. And S duality is so named for the scattering that it describes. The T matrix might be described as a transition, like the optic theorem amplitude. You have your scattering of a theory of the stuff you found from that. You have this idea of a T-duality. So really what it's doing is just relating two theories together. It's your structure that allows you to have two different descriptions of the same theory, and then you can pick from whichever side you need that you have the correct values to match up to make sure what you're doing is actually describing reality. So this is sort of a way to suggest possible scenarios where classical notions of geometry break down in a theory. And we're talking about theories that are of the Planck scale physics, because that's where all the action is. So these relationships described by this T-duality or the T-matrices are important for other reasons in math too. It's just math when it comes down to it. But we're talking about T-duality as it applies to string theories. And so it's basically a target space duality is really what the T stands for. It was noted by Bella Satyanpalan back in 87. It was sort of obscure, so it didn't really get applied till somebody found it and realized it was the same thing. This was actually how Edward Witten combined the 5 major versions of string theory to make it into M theory, which is just what we essentially call the current accepted version of string theory. And we still call it string theory, obviously. And so this T-duality can be closely related to mirror symmetry, and that has other important applications. But come on, we're not going to get too far into this enumerative of algebraic geometry bullshit. So it's an example of general duality in physics. So that's what this wave-particle duality is. That's what this stuff is with dualities. It gets very complicated because it's like this circle is 360 degrees and then this other one wraps around twice and is 720 degrees. So they're still equivalent because they're still 0 degrees, 360 degrees, 720 degrees, etc.
I see. So theoretically, if you knew the speed and direction of all the spins of each constituent section, you can determine if one grid of reality is the same as another or not. You can see if it varies or if it is invariant.
These quantized momenta and other things that they do within these equations are actually how they can describe them as a duality.
The transitioning relationship.
Transition and how it relates to the S duality. Some of these techniques were how Witten and others were able to consolidate the various string theory approaches, consolidate that a lot of people had worked on and that were making the most sense. Consolidate essentially these ideas of strings, the values of a string, the length of it, consolidate, and the tension is going to give your mass of the particle that you're talking about, if it's a mass particle. We can get deeper into this, but what they do is 9 space, 1 time, 1 m, and they applied all kinds of different methods to try to see if they can explain the standard model of particle physics with the mathematical structures of string theory and the deductions made thereof.
But have they actually seen these particles?
I honestly don't even know, because you realize that these particles that they are seeing, they are calculating. I should go into the depths of the actual atom smashing, proton smashing stuff to see, so you can understand. I think we're about 20 measures of magnitude off. Something where we just can't do it. And that doesn't sound like a lot, but it's a lot at that scale. There is incompleteness written all over this theory, which is why they tweak the 19 known constants. Some of those are like the mass of an electron and gravitational constant, background radiation, and other things like that, expansion rate, etc., etc. But
there are actually several more constants.
That's what they do. They try to explain everything with this grandiose theory, but we need to be able to come up with some predictions. So
they mess with the values in the standard model, not in string theory itself.
They say that there's no way to test this stuff, but there's got to be a way to test this stuff. These mesons, these quarks and antiquarks, all these other particles that are in the standard model. I'm going to have to go over the standard model in an entire episode because there are a lot of particles, theoretical particles, other such and suches. I'm going to get the main point of them so that we can tell the difference. For the time being, I just want to briefly touch upon what exactly this string theory shit is and try to go into a little bit more detail into how this theory can give our expectation values. There are actually way more practical ways to get things done. Quantum chromodynamics. What does it do? Actual quantum chromodynamics, though, it studies the strong interaction between quarks and gluons. And they make up our composite hadrons, like our proton and our neutron and our pion, called bosonic theories, and we don't really care about this and stuff. So this main thing that was really done in the late 90s was them finding the relationship between anti-de space, conformal theory, correspondence, and string theory. The quantum field theory is a theoretical framework in and of itself that attempts to combine classical field theory and quantum mechanics. But of course, as with a lot of these other theories, they leave out general relativity and how it describes gravity. So with some of these things, they are able to build these physical models of all these crazy subatomic particles, the stuff dealing with T and S duality.
And what else?
Even U duality. They also got this F theory part too. Even further revisions. That's Qumran-Vafa stuff. Fibered Calabi-Yao fourfolds.
Okay.
Pretty specific with the shapes of some of this stuff. But what kind of differences can these theories have? Okay, a string can either be closed or open. Heteric string is closed.
You should get back into dualities.
Okay, what dualities are, what branes are, short for membranes, which essentially would be 2D. Boltzmann back in the end of the 19th century. Stuff when they were figuring out electromagnetic properties. Boltzmann. This description of entropy using natural logs, which is base E. They can use this to figure out precisely how much entropy is in a system. We have these issues with these black holes. Hawking took an interest in that. Hawking suggested that the surface area of the event horizon of a black hole is proportional in some way to the entropy inside the black hole. So how much entropy? It can only have as much as something that is proportional to the surface area, right?
Right.
Because how big is it? Well, how big is it? How far does it warp space of the event horizon? That pretty much gives you that. They actually got a good formula to find out the entropy. That's interesting. That's something that came largely from Hawking's work.
Black hole physics is much more difficult than you think.
It's the Bekenstein-Hawking formula. And so Andrew Strominger and Qumran-Vafa, they brought this to string theory. How can you derive a formula for some black holes using frameworks from string theory? They have different types of membranes and strings and stuff. So one of them called a D-brane, fluctuating membrane, weakly interacting.
D-branes just specify the boundary of the partial differential equation describing a specific situation.
So where did this stuff start? Gunnar Nordstrom, Finnish dude. He had an attempt on a theory of gravitation. He's like the Einstein of Finland. Like, what the fuck? Obviously, these were further refined down the road. So this Nordstrom guy, he was attempting to unify the electromagnetic force and his theory of gravity. But obviously Einstein, his theory was proven correct in 1919. So he was world renowned for his theory of relativity, which we still use today. After this, Theodor Kaluza put this fifth dimension stuff with general relativity. And so that guy was pretty damn important too. Don't forget him. Kaluza's usually credited with this. But in 26, Oscar Klein gave a physical interpretation of these unobservable extra dimensions. Who cares? Who cares? Who cares? Who cares? Like being wrapped in a small fold. So that's the start. And, all these guys are aware of this thing coming to light, the first superstring revolution and the second one. There's some important guys here. Early 80s, Edward Winton discovered most of the theories could not deal with this chiral phenomena. We got to do an episode on that as well. Chirality, quantum chirality, that's up on the list. And so that's where you don't have an identical mirror image. We're worried about the handedness of the spins, the helicity of some of these particles. That's what the chirality is. So if something changes from that symmetry transformation, that would be called its parity transformation. What is this stuff? Chirality, chiral symmetry. So we're dealing with Dirac fermions here, half spin particles. It's a half spin from its antiparticle. And so they think that possibly all fermions fall under this, but if not that, the vast majority. So the helicity of a particle is positive when it's right-handed, if the direction of the spin is the same as its motion. So if it's different from its motion, then it's left-handed, quote-unquote left-handed. So we're not going to go too far into that. We don't want to talk about U and D quarks and all the crazy shit. Fuck that. Okay, so this first superstring revolution. What these phases and revolutions and stuff are really describing is the amount of research that's being done and the papers that are coming out and what connections are being made between what fields of science. There were a lot of people who worked on this stuff. There was Joseph Polchinski. He wrote a textbook on string theory in 98, deals with D-branes. He contributed those. In 2008, he got that Dirac medal, pretty much a medal for work in physics or chemistry or mathematics or whatever, for work on superstring theory. So that's pretty important. He also got the Fundamental Physics Prize. There's also that Polchinski's paradox. He even has a paradox named after him. This is a take on, you can bounce balls off each other at a certain angle to bounce back. You've seen that with pool balls plenty of times. You throw a ball into the event horizon of a wormhole in the form of like a Stargate or something. It goes through the wormhole, but when it comes out of the wormhole, it is at specifically the angle where it bounces off of itself, which essentially would make it never having gone through in the first place. And so this wormhole, let's say it goes back in time. You shoot the box through there. It exits the wormhole at just the right angle. It collides with its earlier self and it knocks itself off course. And then it never entered the wormhole in the first place. So kind of just a cool little paradox to help you remember that guy, D-brain guy. Let's see here. 5 types of string theories that were becoming prevalent were type 1, and then type 2A, and then type 2B, and then E8 by E8 heteric, and then SO32 heteric. So the sheets propagate through this new space-time, this 11D supergravity. Its implications are profound, and there's no amount of information you can learn to understand this stuff.
There really is a colossal amount of information that needs to be understood in order to grasp this idea of string theory.
You guys have been working on it for many years.
It has been around for many decades, yes, and there still is not a consensus as to which flavor of the theory is correct. Just understand that the idea of holography is at the center of our current understanding. Maybe they can learn more by listening to you. I know that people hated hearing my robot voice, but it's not like I could help it.
We are only briefly going over this now. Each 10 episodes, we are trying to solve this theory of everything. Each 10 episodes. We're taking a small approach each time and getting more into it each additional 10. So for now, this is all I'm going to say on string theory. We will get into the specifics of chirality and a de Sitter space, Poisson's equation, Laplace's equation, and Hilbert spaces, S-duality, T-duality, how these lengths of these strings and the oscillations of the strings affect the particles from the standard model, and how they keep constantly adjusting the values of these 19 constants just to fit in their equations.
The standard model is a tricky business.
It just does not seem like this is something that'll work. I think the standard model is just a little bit off. It needs to be edited. Obviously, there's a lot of true stuff in there. They have seen these particles, but a certain in-depth study needs to be taken at the science that came from those collisions and many of the other collisions that have happened in the last 3 decades. They did some groundbreaking work back when they only could get particles to go 4% the speed of light in the 80s. The cyclotrons back then were nowhere near the speed of light. That's a problem. So it took them a long, long time to figure it out. For now, this is all we're going to go into, and next time we will take a look at maybe a slightly less daunting theory because there's not as much made-up jargon in this shit. That one's more of a method than it is a theory, but we will take a look at that next time. So for now, that is it for episode 18, String Theory of Quantum Foam.
Quantum foam.
The zeroth wave disclaimer.
The views and opinions expressed in this podcast are those of the author or authors and do not necessarily reflect the particular views, thoughts, or opinions of Zeroth Wave Productions, any of its sister companies, its parent company, Zeroth Enterprises, or any other entity which had existed, will exist, or which, quote-unquote, presently must exist outside the realm of our current space-time.
Quantum Foam is produced by Zeroth Wave Productions.